topic of this conversation is going to be on alcohol dehydration reactions as we continue and wrap up chapter 7. So first, let's take a look at this term alcohol dehydration reaction. So of course, alcohol is referring to an alcohol functional group, and that alcohol functional group particularly is in the reactant. When we say dehydration, what we're referring to is that during the course of the reaction, water, H2O, is lost. So in other words, what's going to happen here is that water is going to be a product of the reaction. Just as when you become dehydrated, you lose water, the alcohol dehydration reaction as it proceeds is losing water. Water is a product of the reaction. Following the theme of chapter 7 and looking at the reactions that form alkenes, alcohol dehydration is going to be another example of reaction type that yields alkenes. And we're going to see that this reaction type has some parallels to the E1 reaction type that we talked about in our last segment, where we could describe the alcohol dehydration in many ways as being an elimination reaction, where we're eliminating water from the molecule. We say alcohol dehydration more specifically because of the fact that we are specifically losing water from the molecule during the course of this dehydration reaction. So what's going to happen to lay out the generalities of the alcohol dehydration is we're going to have a molecule that has an alcohol functional group, and we'll put in R groups here indicating this could be whatever we want there. And then we, much like in the case of the elimination reactions, have to have at the beta position a hydrogen available. If this adjacent carbon, the carbon right here, if this were a quaternary carbon where there were no hydrogens available at any of these adjacent carbons, then the reaction would not be able to take place, because during the course of this reaction, what's going to be lost is going to be this hydroxy group and the hydrogen from the adjacent carbon atom, that beta hydrogen, using the terminology that we used in the elimination reaction. So that's where we get the loss of water, is via the loss of a hydrogen and a hydroxy group from the molecule. When those are lost, in their place is going to be an alkene group so that we're able to fill the octet for both of those carbon atoms. So we're going to get a carbon-carbon double bond going on in our final product. And those R groups are carbon-carbon bonds or carbon-hydrogen bonds. They're indicated by R, are going to remain the same. This particular reaction is catalyzed by an acid. And the particular acids that are commonly used here are often sulfuric acid, which is H2SO4, or alternatively phosphoric acid, H3PO4. Oftentimes, rather than specifying that it's sulfuric acid or phosphoric acid, since there are many possible options of acids to use here, sometimes it's just specified as above the area you'll see the term acid catalyst written. And that just indicates that there's a source of protons readily available in the reaction for it to take place. And you can also sometimes see this as H plus or H3O plus. The idea is that there will be an acid there available as a catalyst. By definition, the catalyst is going to be a substance that lowers the activation energy of the reaction to allow the reaction to proceed more rapidly. The way that the acid catalyst is going to do that is at one step of the reaction mechanism, it's going to be consumed, and at another step later on, it's going to be reformed. So overall, the concentration of the catalyst, when we go from the start of the reaction to the very end of the reaction, is not going to change. If we were to monitor the pH of the reaction, we would see that it would remain the same, indicating that the acid catalyst, the acid had not accumulated or been depleted over the course of the reaction. Instead, overall, its concentration is going to stay constant because of the fact that when we start to dig into the mechanism of this, we're going to see that the catalyst is consumed at an early step of the mechanism, and then at a later step, it's going to be regenerated. So let's take a look at what's going on in the acid-catalyzed dehydration reaction from the perspective of the mechanism of this particular reaction. So we'll take a look at it for an example problem here. So go ahead and start off with this molecule. And we're going to react with our acid catalyst. So I'll just throw in phosphoric acid here. This could be any acid. You just need to recognize that there is an acid present there and recognize that that's going to be acting as our catalyst. And so what we're going to do is walk through the mechanism for this reaction. That is the step-by-step series of electron transfers that have to occur to go from reactant to final product. And we're going to use that mechanism to predict the final product of this particular reaction. Now, when it's time to write mechanisms that involve acids, such as phosphoric acid or sulfuric acid, where the acid is primarily serving as a proton donor to speed up the rate of the reaction, generally it is going to be fine for purposes of the mechanism to just put H plus as your abbreviation rather than writing out the full Lewis structure for H3PO4 every single time, since the main portion of this, the business end of the molecule, is going to be that proton donation that it's going to be able to do. So let's take a look at the mechanism for this reaction. And what I want you to know and become aware of from here on out is that if you see an acid starting material in the reaction, generally what's going to happen in the very first step of the mechanism is that the other reactant is going to pick up a proton. The other reactant, we could say, is protonated. So anytime, not just for this particular reaction, but more broadly across reactions that we'll see all semester long, if there's an acid present in the starting materials, you want to try to use that as early in the mechanism as possible because acids tend to react very quickly. And so it's going to be a very fast reaction step to take us forward. So if there's an acid present, use it at the very first step of the mechanism, if at all possible. And this is going to be a general rule, not just something that applies to situations of acid-catalyzed dehydration reactions, such as we're doing here. But in general, when you're looking at a reaction, a good hack is to observe if there's an acid present. Acid-based reactions are very quick, and so you're going to expect that the protonation step, the protonation of the organic reactant, is going to happen first off. So we're going to go ahead in and fill out the first step of this mechanism, since we do see an acid reactant there, is going to be protonation. When we say that the step is protonation, what we're referring to is that the organic reactant picks up a proton. It's going to gain a proton during this step of the reaction. So we'll go ahead and write in our organic reactant. And now we think back to our previous chapters when we were looking at acid-base reactions, and we thought about what enables a molecule to act as a base to pick up a proton from an acid. And what we saw back then was that to be able to act as a base, the organic molecule needs to have either lone pair electrons or pi bonds. And so we look for lone pair electrons or pi bonds in our starting structure here. And that's going to be what is going to be susceptible to picking up that proton. So we're going to abbreviate our phosphoric acid as just H plus because that's going to be the ultimate business end of the phosphoric acid molecule. It's going to act as a proton donor, our acid. And then the only option we have here for what can act as a base in our starting material is going to be that oxygen atom, because the oxygen is our only location of lone pair electrons or pi bonds there. So we'll go ahead and use those lone pair electrons to create a new oxygen-hydrogen bond in this acid-base reaction, or the protonation step as we call it. So we're protonating the oxygen. So we protonate the oxygen. I'll show that new covalent bond in blue attached to our green hydrogen atom that we just picked up from that phosphoric acid from our proton donor. Now, if we look at the formal charge that's going to be here, we have to have a positive formal charge on the oxygen atom now. What we've done as a result of this protonation step is we've created a much better leaving group than was possible before. Because if we break away now that carbon-oxygen bond, the product of that step is going to be water. Whereas if we looked back at the original starting material where we had an alcohol functional group there, if we broke away that alcohol functional group, the product of that step would be a hydroxide anion. A hydroxide anion is really unstable relative to water. Water is much more stable. And so by protonating here at the first step, that's going to enable in the second step for water to be the leaving group. And that's going to be a much more favorable situation than having the hydroxide group try to leave on its own prior to being protonated. The hydroxide group is not a particularly good leaving group, on its own because of the fact that the product of that step would be quite unstable. So instead we do the protonation first, and that's why this reaction is going to be catalyzed by the acid, because the fact that we're able to protonate there is going to create a much better leaving group. A better leaving group is going to leave faster, and that's going to speed up the entire reaction process. So step 2 then is that the leaving group leaves. So we could think of that protonation step at step 1 as really priming the reaction. It is going to enable water to act as a leaving group, creating a much more favorable situation here at step 2 of the mechanism. So it's going to make step 2 of the mechanism much less of a bottleneck than it was before. Step 2 is going to go much faster, and that's going to enhance the overall rate of the reaction, since step 2, where the leaving group breaks away, was the rate limiting step of the mechanism. So leaving group has left now. That leaves us with a carbocation, and that gives us our water product, relatively stabilized water. And now we have a carbocation intermediate. And when we have carbocation intermediates, we look at ways to stabilize those, because a carbocation intermediate is a relatively unstable intermediate here. We think about ways to stabilize intermediates as being either resonance or induction. We have no opportunity for resonance here, and so we turn to induction and how we can maximize that. And we have here a secondary carbocation, and we could increase the opportunity for induction here if we could convert this into a tertiary carbocation. And so this brings us back to a theme that we've seen occurring over and over again for both the E1 and SN1 reactions, where we can have a carbocation rearrangement, or a 1-2 shift if you like, to enable the further stabilization of this secondary carbocation by converting it into a tertiary carbocation, which will have more electron donating alkyl groups associated with it. So leaving group is left at step 2 to make that carbocation. Step 3 is that we get the 1-2 shift to give a more stabilized carbocation. Okay, so our 1-2 shift here, what we'll do is I'll go ahead and fill in our hydrogen atoms that are present in our structure. So we have a hydrogen atom there, and we have a hydrogen atom here. And so if we take the hydrogen atom from right here, doing our 1-2 shift, where we bring that over one spot, indicated with our arrow here, we take the covalent bond over, that's going to give us CH2 group and allow us to create a tertiary carbocation. So I'll go ahead and redraw in our skeleton here. And now in our skeleton, we would have the 2 hydrogen atoms here and here, and the methyl group is still right there. And now if we look at where our positive formal charge is going to have to be, it's going to have to be right here. And that's allowed us to create a tertiary carbocation out of a secondary carbocation. Tertiary definitely more favorable than secondary. So this is going to be an energetically favorable step, this 1-2 shift. So that's something to look for if we're using induction to stabilize here at this step. We want to maximize that induction by doing the 1-2 shift. Then at this point, we're going to carry out an elimination reaction that's going to be quite reminiscent of the E1 reaction that we saw when we were working with molecules that had halogen leaving groups. So here at step 4 then, what's going to happen is that we're going to get beta elimination of a proton to give an alkene. And the beta elimination occurs due to a base grabbing that proton. So we're thinking here now of the tertiary carbocation acting as the acid. Particularly, it's going to be the hydrogens outlined in green there that will act as the acidic hydrogens. And we'll have a base come in and grab those. And so that raises the question of what can act as a base. So it does not require a very strong base at all here to grab that proton, because of the fact that we're working with a rather unstable carbocation. The carbocation is certainly only going to be transiently present during this reaction. Its end game is to get to a stable final product. So the beta elimination, the base that we can use here, can either be the water that we generated earlier in the reaction of that previous step where the leaving group left, or it can also be the conjugate base of the phosphoric acid that we started with. Either one of these will work. Really, we just need a source of lone pair electrons to grab a proton from this acid. So I'll go ahead and use water here. So we'll plug in our H2O. H2O is able to act as the base here because of the fact that we don't need a strong base to grab that proton because of the fact that this is an unstable starting material. When we finish this reaction, we're going to have a much more stable product. So this beta elimination should look a lot like what you saw in the E1, pretty much exact, with the base grabbing a proton from the organic acid, the carbon-hydrogen bond breaking and coming over to make your carbon-carbon double bond of the alkene. So we'll go ahead and draw in what would result from those electron pushing arrows that we showed. Now our double bond right here, our methyl group coming off like so, and then we would also be generating H3O plus as a result of this step. And when we see H3O plus, we can really think of that as being synonymous with H2O plus a proton. And so this is where we get the regeneration of the acid that we used in the very first step. So here the acid is regenerated. And that's why we would define this reaction as being acid catalyzed, because if we look at the whole mechanism, what we see is that at the early stage of the reaction, a proton is used, and at the last step of the reaction, a proton is generated. So the net here is a net gain or loss of 0 protons. So hence, that's why we call it acid catalyzed. And we're going to see that this is a very common theme that we'll come across in organic reactions, is that in acid catalyzed mechanisms, we'll see that at the very first step of the mechanism, up here, the acid is consumed in a step we would describe as protonation, because we're saying that the organic molecule is picking up a proton. And then at the very last step of the mechanism, we see that the acid is a product of that step. The acid is being regenerated, and that's why we call it a catalyzed reaction. We'd call this last step beta elimination, or we could also call it deprotonation because we're losing a proton during that step. So we're going to see this theme over and over and over again. And so it's a really good idea to get super familiar with this general idea that if there is an acid present in your reaction, you want to always look for a way, if possible, to use it at the very first step of the mechanism. And it's going to be possible to use it at the first step as long as there's a pi bond there or a hydroxy group. That is going to allow you to use that acid at the very first step of the mechanism. So let's take a look now at another example of an acid-catalyzed dehydration reaction. And in this reaction, what we're going to be given is our starting material and our final product of this reaction. We're going to be asked to provide a mechanism to show how we would get that particular product out of the reaction. So we'll go ahead and take our starting structure here. So we're going to start with this molecule, and we're going to react with sulfuric acid, H2SO4. And we'll go ahead and say there's water also available in the reaction mixture, potentially there as a solvent. And then the product of this reaction is going to correspond to this crazy critter. So we've gone ahead and made the product of the reaction. We're asking for the mechanism to show how we would get to that particular product. And I will say that in this particular reaction, the actual case is that this reaction yields multiple products. But we're asked to provide the mechanism to show how to get this particular structure. This is our final product. And so we have to ask how we're going to go about doing that using the knowledge that we've accumulated so far this semester, in particular that dehydration reaction we've been talking about as the centerpiece of our operation here. So let's go ahead and walk through the mechanism to get to the final product. How are we going to make our necessary carbon-carbon bonds there and alkene group to get from our starting material to our final product? So we go back to what we talked about a little bit earlier about if there's an acid present, use it at the first step of the mechanism. So let's go ahead and see what we can do here by using that acid at the first step of the mechanism to get things going using the understanding we've developed of these dehydration reactions. So the first step of the mechanism, we're going to take our organic starting material, that is our 6-atom ring that has that hydroxy functional group on it. And we're going to bring in our acid, which again, whenever you're writing out mechanisms, you're welcome to, rather than draw out the full Lewis structure of sulfuric acid, you're welcome to instead just abbreviate as H+, or if you're more comfortable with H3O+ is fine as well. And at the first step of the mechanism, since we have acid there, I am always going to label that as protonation, as long as there is something about the organic structure that can pick up a proton. So we'll go ahead and, in following the acid-catalyzed dehydration route, the lone pair electrons from the oxygen are pretty keen on picking up a proton. So we'll go ahead and protonate that oxygen atom as the first step of the mechanism. And we need to plug in our positive formal charge there. Like so. And now that brings us to our second step. So what we've done in that first step, by bringing in the proton, is we have created a much better leaving group than was available previously. And so with that leaving group in place, what's going to happen next is the leaving group is going to break away. So we're following, thus far, the mechanism that we saw above for just a standard acid-catalyzed dehydration. So second step is the leaving group breaks away. Leaving us with our carbocation intermediate. And that's going to put our positive formal charge right here. So what we might then think of doing here, if we were predicting one of the possible products, would be to do an elimination reaction at a beta position. So right here would be the most substituted beta carbon. So that would lead to our favored Zaitsev product, as we do with these elimination type reactions, including the alcohol dehydration. So we could remove the proton there in green and create an alkene group. However, our final product has this extra ring structure in place. If we look back at what we're aiming to create here in this reaction, we see that we really need to aim to make a second ring in there. And if we merely remove the proton shown in green and create an alkene group, that's going to give us a final stable product with no formal charges that it's hard to see how that's going to then continue to react to give us the product circled in yellow. Once we formed a relatively stable final product, what's going to be the impetus to continue onward? So we need a way here, rather than finishing this reaction up right now and giving our final product in one step, we need a way to make that ring structure, the second 5-membered ring. So we need to think about how we could go about doing that based on what we know about the behavior of acids and bases, nucleophiles, and electrophiles. So as we have this molecule set up, when we look at what we have available here, we have pi electrons over here as part of this alkene group. And we've talked previously about the potential nucleophiles in reactions can be either pi electrons or lone pairs. So pi electrons or lone pairs can act as nucleophiles. And so if we're thinking about how we can make a 5-membered ring within this molecule, we need some way to make a 5-membered ring because that's what we see in our final product up here, outlined in green there, that 5-membered alkene ring. One way that we can envision doing this is to have the pi bond act as a nucleophile and attack the electrophilic carbocation. So we have the electrons come from the pi bond over to here to attack, And lo and behold, that could create for us a 5-membered ring. That 5-membered ring, I'm going to just number off for you here, arbitrarily just marking off the carbon atoms. 1, 2, 3, 4, 5. So if we have carbon number 1 as the location where the pi electrons begin, and those pi electrons attack carbon number 5, that's going to create a new covalent bond between carbon 1 and carbon 5 via the pi electrons acting as our nucleophile here. And that's going to be the pivotal point of this, because that's going to give us our 5-carbon ring that we need based on the product that we're trying to justify how we get to. This is not necessarily the major product of the reaction, but it's one of the products that we've observed. And so we need a way to justify how we got that product. So let's go ahead and draw what would result from that. What I'm also going to do here to kind of help us with our molecular bookkeeping is to just fill in some of the hydrogen atoms here. So that'd be a CH2 group at the end of that alkene bond. At carbon 2, we have just a carbon bonded to the 2 alkyl groups. That would fill the octet there. Carbon 3 is a CH2 group. Carbon 4 has to be a CH group. And carbon 5, we have everything already shown there. That's our carbocation. So let's go ahead and draw the scaffold of the molecule, the carbon-carbon bonds, that would result from making that link between carbon 1, or what we were calling carbon 1, and carbon 5. And I'm going to show that link in green here. So we're joining what was carbon 1 with carbon 5. And I can mark these in this newly formed ring here, just to help you keep track of who's where in this. And we can use this as a tool also to help us fill in the other groups that are bonded here. So at carbon 2, we previously saw that there was a methyl group bonded there. This methyl group here at the end. And so that has to still be there after that step. We haven't done anything to break that carbon-carbon bond. So we're just trying to systematically go through and map out who's where at the end of this reaction step. So this carbon number 1 has to still be a CH2 group because it was a CH2 group over here. Carbon 2, now that the pi bond is no longer there, rather than carbon number 2 having 4 bonds to it, it's only going to have 3 bonds. And so that means that carbon number 2 has to be a carbocation. Nothing has happened at carbon number 3. So carbon number 3 is still going to be a CH2 group. Carbon number 4 is still a CH group. Carbon 5 is now a carbon that has a complete octet because it had the 3 alkyl groups bonded to it to start with, and now it's got that 4th bond in green to make a 4th bond to connect the ring. So we would describe this step as an intramolecular reaction where the nucleophile attacks the electrophile. So the pi bond is going to act as a nucleophile to attack the carbocation. And this is going to be particularly favorable in cases where 5 or 6 atom rings result from this, because 5 and 6 atom rings are going to be the most stable motif because of the relatively favorable bond angles. When we have a 5 or 6 atom ring, the bond angles are going to be relatively approximate to the ideal 109.5 degree angle in the final product for the sp3 carbons of the ring. So the pi bond is acting as a nucleophile to attack the carbocation. That's going to give us this intermediate shown here. And then to finalize this product, we need some way to form that alkene group that's observed in our final product up here at the top right corner. And so we need to work on a strategy for getting to that. So go ahead and draw in our next step here. And now that we have the reaction set up with a carbocation within that ring, this leads us to draw some parallels to the standard dehydration reaction where we remove a proton from the beta position. And so that's exactly what we're going to do here is beta elimination of a proton to give an alkene. And this is completely analogous to the last step of that dehydration reaction we looked at before. And we're justifying how to make this yellow circled product in the upper right corner in particular, so that drives where we need to remove a proton in order to do that. And it just so happens the proton we'll need to remove in order to do that. It's going to be one of these protons right here. So I'm going to erase that CH2 and draw it out explicitly so that we can show the mechanism happening here. We can show the attack on one of those 2 hydrogens. And as we saw previously, the attack on either of those protons is very effective. And so we just need the conjugate base of our acid, so the conjugate base of sulfuric acid, since sulfuric acid is what we're using, or water to act here as the base. We have water available, certainly. I'm just going to use that as the base, and that's going to come in and grab the proton from that beta position, resulting in the carbon-hydrogen bond electrons coming over to make the pi bond, and that's going to give us our final product, which will have no formal charges anywhere within our organic product. And that's an indication to us they've probably reached the end of the road here, a good stopping point for the reaction. So I'm going to fill in my 5-membered ring, make sure I'm keeping all those groups on there that were there to start with, and our double covalent bond is going to end up right there. We'd also create H3O plus out of this step, so this step is regenerating our acid catalyst as well, which we used at the step 1 of protonation. So let's just double check that our structure here that we've created does indeed match the one that we were targeting in this mechanism. So we've justified how we would go about making this final product through pretty much the series of acid catalyzed dehydration steps of protonation, leaving group leaves, and beta elimination. And we've just added in this extra fun step 3 here to illustrate how we get that extra ring forming. We're using the logic here that electron sources, that is nucleophiles, that is pi bonds, which we see here, or lone pair electrons, are very drawn to electrophiles, that is carbocations such as here. And so when those are in really close proximity in the molecule, what we end up getting is the so-called intramolecular reaction. So this step right here we would describe as an intramolecular step. It's called intramolecular because the two reactants are present within the same molecule. So typically the reactions we look at are intermolecular, meaning between two different molecules coming together. This is intra because the nucleophile and the electrophile are both in the same molecule. So typically intramolecular reactions yield rings. So if you're looking at ways to make a new ring within the molecule, generally how that happens is through the so-called intramolecular reactions. We're getting an intramolecular reaction here by having the nucleophile attack the electrophile in the same molecule. So that pretty much wraps up our discussion of alcohol dehydration reactions, and that finishes up our coverage of Chapter 7. Chapter 7 worksheet will be available to you on Canvas, so be looking for that, and we'll continue then onward with Chapter 8 when we meet up in the next class period, looking at reactions of alkanes. So in Chapter 7, we've talked about ways to make alkenes. In Chapter 8, we're going to talk about once you've made alkenes, what can we do with those alkenes in terms of what reactions will they be able to undergo. So we'll go ahead and continue with that next class period.